is on set theory, and we're actually going to do this in 2 days. Otherwise it gets a little bit overwhelming. There's a lot of terms to know here, so I want to kind of split it up for you. Alright, we better start by talking about what a set is. I believe we already talked about this last day. A set is a collection of distinguishable objects, and they don't have to be mathematical objects. I mean, you could talk about the set of clothing items, and then you could make a list of all the items: pants, shirt, hat, tie. You go on and on and on, right? But often what we do in mathematics is we use numbers for our sets. So here's an example: the set of whole numbers. Let's call the set W. The way you often designate a set, you don't have to, but what we usually do is we use a capital letter to show that we're talking about a set. And here we go, we're going to write the set of whole numbers. So the other way you show a set is you use curly brackets, or braces they're called. So our set in this case whole numbers starts with 0, and then 1, and then 2, and then 3, and then it keeps going and going and going, doesn't it? But we don't want to write them all. We can't write them all, so we put dot, 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 and close the curly brackets, and you're done. So again, these curly brackets are used to designate a set, and the way you say this, like when you see the curly brackets, it is the set of. That's how you read that. So the set W is equal to the set of 0, 1, 2, 3, and on and on and on and on. Alright, the things in the set are called elements. So that's any object in the set is called an element. So in this case, for example, in set W, which we've already talked about up here, 16 is an element of set W, isn't it? But negative 16 is not an element, right? Negative 16 is not included in these curly brackets here. So the way we show that something is an element is we can say that 16 is an element of W. But negative 16 is not an element of W, of set W. Okay, that is the way you represent those two statements. So there's 3 ways to define the contents of a set. One way, and that's what I did up here, is you just list the actual elements. So let's do a different example here. Let's use, well, I'll just make one up. Let's call it set A, and let's say that set A is equal to 0, 1, 2, 3, 4, 5, 6, 7. That's set A. So one way you can do is you can just write out all the elements. Now it's not going to work very well though if it's some massive set, right? If there was tens of thousands of elements, you don't want to have to write them all out. So we need some other ways of defining the contents of a set. Another thing you can do is you can describe it in words. So there's different ways you could do that. One way I could do it is I could say that A is equal to the whole numbers. Since it includes 0, I'll say the whole numbers. I could say up to and including 7, or I could say the whole numbers less than 8. So again, there's often multiple ways to describe the same set. And the third way, gets a little bit more complicated, more mathematical looking I suppose, is you use set builder notation. And the way that would look, if I'm talking about this same set, is I would say A is equal to curly bracket. Remember, curly bracket means the set of. So A is equal to the set of X. And I put this vertical line. And what this vertical line means, the way you read that, is such that, such that. So what we have is A is equal to the set of X such that X is less than 8. But that's not enough just to say X is less than 8, because then you'd include numbers like -4, -3. It would also include decimals, which we don't want to include. So we have to also say that X is an element of the set of whole numbers, which is W. That's the set of whole numbers, W. Okay, just so you know, n is equal to the natural numbers. that's 1, 2, 3, 4, 5, dot, dot, dot. W is equal to the whole numbers. This is the set of whole numbers. So these are very common ways of representing natural numbers. The set of whole numbers is with a W. Z represents integers. The set of integers is with Z. I believe it stands for Zahlen, Z-A-H-L-E-N. R, which you often put with the double line there, that's the set of real numbers. And that's probably all the ones you need to worry about. Oh, wait a minute. Rational numbers are represented with a Q. So remember, rational numbers are any numbers that can be written as a fraction. And irrational numbers, numbers like pi and the square root of 2, they're represented with an I. These, you're not going to worry about this very often. The ones you're mostly going to worry about are going to have to deal with are these first three up here. But anyway, just to speed things up for you, sometimes when you're writing using set builder notation, these are accepted mathematical ways of representing sets. Okay, so the number of elements in a set. Let's define a set first of all. Let's say that set D is equal to the set of all digits. And I tell you what, we're going to use the set of all digits down here as well. So let's just write that set, the set of all digits. What's the set of all digits look like? It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all digits. What's the only other digit there is? 0. These are digits, right? All the numbers are made up out of these digits. So if I want to know the number of elements in this set, this is a complete set, there's no more. The way I represent that is small n, and then the D, the capital D, remember capital represents sets. So it's kind of like the number of elements in D, and as we've written here, the number of elements in D is 10. That's the way you represent how many elements there are in a set. Okay, next, the universal set, which is also called the sample space. The universal set is the set of all the elements under consideration. So, for example, in the set of digits, this is the universal set. This is all of them. But then you could be talking about just some of them, right? Maybe there's a set P, which is just equal to 1, 4, and 5, or something like this. But this is the universal set for digits. If I was talking about the universal set for provinces, how many would we have? There'd be 10, right? And you'd list them all: British Columbia, Alberta, Manitoba, etc., etc., etc. And you can't always count all the elements in the universal set. There might be too many to count. If we're talking about the set of rational numbers or real numbers or something like that, we can't sit there counting them all. There's just too many. Okay, now that we've talked about universal sets, we can talk about subsets. Because what a subset is, it's a set whose elements belong to another set. So it's like a part of another set. Let's give you an example there. I'm going to call a set, I'll call it set A, and let's say that set A is equal to 2, 5, 8, and 23. I'm just making up those numbers just randomly. Now, do you see that all those numbers are whole numbers? But is that all the whole numbers? No, not even close. So this is a subset of set W, where set W, remember, is the set of whole numbers. The way we show that mathematically or quickly is we say A is a subset of W. Kind of looks like a C, but that means subset. Let's call another set B, and let's use numbers like -3, -2, -1, 0, and 1. Now, are all those whole numbers? No. So B is not a subset of set W. And the way we show that is we say that B is not a subset of W. It's not a subset of the whole numbers. Okay, a few other things. All sets are subsets of the universal set. So any set that you write down, it's always going to be a subset of the universal set, which makes sense because the universal set contains every element that you're interested in. Every set is a subset of itself. So if one set is if set A is 2, 5, 8, 23, and then we consider the set 2, 5, 8, 23, it's exactly equal, right? Well, they're subsets of each other. Every set is a subset of itself. If you do want to distinguish that, you're like, well, that's not very interesting when they're exactly the same. You can introduce this concept of proper subset, and with a proper subset, it doesn't include the set that's exactly the same of itself. So 2, 5, 8, 23 is a subset of set A, but it's not a proper subset of set A. Okay, I don't think we talk about proper subsets in this workbook or anything, but there is a distinction there. And the last thing I want to say is the empty set is a subset of every set. The empty set, what's that? Well, here we go. The empty set is a set that contains no elements. So I know it's a little strange, but if you consider no elements at all, that's actually a subset of any set. Okay, so the set A here with 2, 5, 8, 23, one of its subsets is a set with no elements at all. And that's always the case. The empty set's always a subset of every set. So the way you represent a empty set is you can either use this notation, which you've used many times for like no solution, and what that means is empty set, there's no answer that works in that case. Or the other way you can do it is you can use your braces, your curly brackets, but you put nothing inside of them. It's literally an empty set. I like that. An example of an empty set would be something like if I asked you to write the set of all even odd numbers. There are no even odd numbers, so you wouldn't be able to write anything. You'd have to write one of these two things that show that's an empty set. There's no elements in that set. Next is the complement of a set. The complement of the set is the set of all elements in the universal set that are not in the set being considered. So it sounds confusing. It's not too bad. For example, let's define the universal set. I'm just going to make one up. If the universal set is D. Remember D was all the digits? So this is the set of digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And let's say that set A is equal to 1, 2, 5, 7, 8, and 9. That's set A. Then the complement of A is, first of all, the way you show a complement is you put A with the prime sign, right? Like that. So A prime, or A complement, is equal to, so what you look for the complement is which numbers are there, which elements are there in the universal set. Remember the universal set was 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, that do not show up in A itself. So 1 shows up, 2 shows up. There's no 3, so that's in the complement. There's no 4, that shows up in the complement. 5, there's no 6, 7, 8, 9, there's no 0. So there you go, that's the complement. By the way, if you take set A and you add A prime, or the complement of A, what does that equal? If you take set A and you add its complement, you get the universal set. I'll just write universal set. Kind of a useful thing to know and to think about. Alright, a few questions here to finish up. Set A equals A, B, C, D, E, F, G. Notice how the elements are usually represented with small letters and the set is represented with a capital letter. That's usually the way it goes. Set B is A, C, G, and set C equals D, H, R. NA, what does that mean? That means the number of elements in A. Well, that's not too hard. You just have to count them up. 1, 2, 3, 4, 5, 6, 7. There we go. The number of elements in B, 1, 2, 3, 4. I didn't even bother with NC because I think we get the concept. Okay, subsets here. Is B a subset of A? So you're asking yourself, are all the elements in B, are they all elements in A, right? Do they all show up in A? A, C, E, G. Yes, they do. So this is a big yes. Now we're looking at the reverse here. Instead of A subset of B subset of A, I'm looking at A subset of B. So order matters here. Do all of these elements, do all 70 of these elements here show up in set B? No way, they don't. There's some of them that just don't show up here. Like B, for example, does not show up there. Is C a subset of A? So does D show up in set A? Yes. Does H show up in set A? No. So already we know the answer is no. Is B a subset of B? Okay, so we're asking is this set here a subset of itself? And remember, every set is a subset of itself, but it's not a proper subset, right? In order to be a proper subset, it can't be exactly the same. Is the empty set a subset of C? Yes, the empty set is a subset of every set. So the empty set is a subset of A, the empty set is a subset of B, the empty set is a subset of C. And finally, if set A is the universal set, so I'm just going to define this as the universal set right here. List the elements of B prime. So here's B, and I want to know what B prime is. Remember, these are all the elements that don't show up, that are part of the universal set, but aren't included in set B. So the universal set has element A, and so does B. It has element B, but the set B doesn't. So B has element C, yes. Has element D, but set B doesn't. Has element E, yes. Has element F, but set B doesn't. And has element G, and yes, set B does have that. So this is your complement right here. B, D, and F do not show up in set B, but they are part of the universal set. Alright, I know it might be hard to believe, but as I said at the start of this chapter, this set theory that we're working on here is actually foundational to mathematics. It's one of the most important things that there is to understand if you were going to pursue higher level mathematics. Okay, even if you're not pursuing higher level mathematics, it's kind of appealing, at least to me, in just the logical thinking it requires. So I hope you feel likewise. Enjoy.